Do you have your own clicker, or do you need a clicker?
Uh, no, I was just going to use.
Okay, you're just gonna use that.
So this is visualization. So it's got.
Can I try it? Like, I mean,
You can. I mean, I
no,
guess
no,
you
no,
can
no,
try
no.
it.
I mean, like
Redo.
on here just to see.
My slides are also done in Keynote, which makes it hard. So I was figuring that I was going to be using my laptop because of the visualization, and
Right,
I
right.
was.
Okay, okay. So what I'm thinking is we just need to use your laptop. When are
Yeah.
you going? Are you going in the second session or the
Like
third?
I'm going right before lunch. I'm going at like 12:50.
Okay. All right. We're just gonna have to do this. So I'll find you a VGA somewhere. Pindar has some.
Okay.
The question is if Anton's gonna like scream at us. We're switching it.
If there's any screaming, you can
Be
make sure
back
it's.
at least 5 minutes before 9. Okay. If
Just
there's
have it directed towards me. I can handle it.
oh.
No, no, no. Internal. External. Advanced switches. Okay, try again. Advanced switches. Yeah, 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 yeah. No, that's still. Hello.
Where is Warren? Where is Warren? I need my signals. You need my okay. I'll give them.
And now we change the pin, right?
Let's see. What mic right now? The equipment's not placed here, so
Ê, tại đi. Tôi tìm hóa tất cả mà. Tìm hóa tất. Tìm hóa sau sen rồi.
One
Testing, testing.
second.
With my
Give me
Tìm hóa
ID.
dùng cái.
Fourth.
Mấy điều so sánh. Ê,
No. This ID. 463. 463 173 895 895. Let's see. 3409. Let's hope this doesn't puke somehow.
let's see if I can make it actually full screen. Let's see. It's on
This is.
on OS 10. It's Command Shift F.
Oh, you can do this there.
Oh, sure. Oh, right. So this is just to.
Yeah, I mean, there's a tiny bit of latency, but
Okay, so I'll just move over to.
let's hide this.
plug it into the camera there.
Okay, then let's switch to full screen mode. a little heavy on the client side.
Yeah, it is. It's like 16 megabytes of JSON on the back end,
No, that's just RAM.
plus like something like 900 megabytes of server side bandwidth. So yeah, it's I can do it. Anyway. So that's what that is. I'm going to receive your
Dạ tầm tầm.
'Testing, testing. Testing, testing, testing. Testing, testing. Testing, testing. Testing, testing, testing. Testing, 1, 2. Testing, 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 1, 2, testing. Testing, 1, 2, testing. Testing, 1, 2, testing. Testing, testing, 1, 2, testing. Testing, 1, 2, 1, 2, 3, testing. Testing. Testing, testing. Testing, testing, 1, 2. Testing, testing, testing. Testing, 1, 2. Testing, testing.
Yeah, totally. We promised it at 8:50 in the start broadcast. And then Ale, do you have your phone with you? Should I send you an email with the link? No. So I can send it to Gmail, right? I think the Wi-Fi is breaking down. Okay, so we need to solve this one.
Turn off the Wi-Fi. Turn off the Wi-Fi.
That's only number one. Who was responsible for?
This is where I am having Windows. Everything okay? The Wi-Fi is coming. So we have LTE. Okay. But I don't know if you turn the Wi-Fi off.
So I can have the MC give an announcement that if you're not actively using the Wi-Fi, please turn off your Wi-Fi. Well, I think the screen would take priority.
Yeah.
Ideally, we would have cable internet, right? We do have a cable, and yeah, both of them are already LTE. It's just a.
The batteries are really nice. They have to probably assign IP or add your MAC address or something. Anton, do you know who's? Hey Jack, now let's take photos here.
Where should we sit?
Anton, do you know who's responsible for internet inside? Bindar. Bindar.
Oh, thank you.
I tried to restart it. It has to like fucking install shit. What do we say? Go. Just I know my tablet that was dead.
There's more seating on this side of the room. There's more seating on this side of the room. You think you smell the Wi-Fi?
Hello, good morning, everyone. 大家早上好.
Hi, welcome to Scaling Bitcoin. We're really excited to have you all here.
My name is Bobby Lee,
And I'm Victoria Van Eyck.
and we're here to kick off the Scaling Bitcoin conference. So let's make the introductions.
Okay, we have Pindar Wong coming up to do some welcome messages.
Pindar is the chairman of the organizing committee. Let's give a big round of welcome to Pindar.
Okay, thank you so much, 大家好. Welcome to Hong Kong. It's lovely to see many of you from Montreal so soon. Rusty, yeah. So what I'm going to be basically doing is reading the house rules. As you know, what we said in Montreal is that we have a 4 Cs. We have a code of conduct, which you should all have been given. Right, that creates a safe space for neutral discussion. Right, no debates, no decisions. And that's hopefully going to foster communication between the speakers, and most importantly, between yourselves. Hopefully that communication results in collaboration, and hopefully that collaboration results in an emergent kind of consensus. That's not up for us, up to us. Consensus is emergent. That's really up to you. So with that, just some house rules. We have, as you know, in the code of conduct, no attribution policy. It's really one rule, which is we have no attribution. And that also includes photographs. Within this room, no photographs, please. With that, I want to pass you to our program chair, Niha Nirua.
Hi, everyone. Thank you so much for being here. So I know that for a lot of you it was a lot of time to get here. For other people taking time on the live stream to participate, we're all here because we care about the future of Bitcoin. And so thank you. And welcome to phase 2 of the Scaling Bitcoin workshop here in Hong Kong. So here's what's really different about phase 2. We're going to evaluate specific design proposals. So whereas phase 1 was really about understanding the problem, phase 2 is about solutions. And that fact went into every aspect of this program design. So we're going to have some BIPs that are already ready to roll, that are already implemented, or could be soon. We're also going to have some presentations that are more forward-looking and about the future of Bitcoin. We're going to have really excellent technical sessions, and we're going to have a panel to learn about the miners. And we're also going to have a lot of dynamic time for discussions to emerge, so we can really talk about these problems and the solutions that are presented today. Now, what's really important to remember is that this is an opportunity. It's not a committee meeting. We're coming together to learn, to evaluate, and to form educated opinions. Implementing solutions that might emerge here still requires time, review, and thorough testing. And so with that, I'd like to introduce the first speaker, Jorge Timon, who's going to be telling us about BIP99 and uncontroversial hard forks. So, Jorge.
Thank you. So, is this working? Oh, yeah. So, we're going to talk about consensus forks, which are changes to the consensus rules. Not everything in Bitcoin are consensus rules, and there's many things that any node can do as they like, but we are going to focus on the consensus rules. And I'm going to give an introduction about basic things, basic classifications and stuff, and then focus on the uncontroversial consensus forks. And the last part is on controversial and disagreements, but I put it the last because maybe I don't have time to go through it. So why do we want to classify consensus forks in the first place? Well, for one thing, we often have long and heated discussions, and many times it's because we don't share a common terminology. We don't have the same definitions, and well, that leads to disagreements. Another advantage of classifying the consensus forks is recommend different deployment strategies for them. And one of the objectives of BIP99 is to make one category that it's uncontroversial hard forks and hopefully deploy one, the first one. So the first classification that it's more commonly used for consensus forks is soft forks versus hard forks. So soft forks limit the rules further. So things that were invalid, they still all remain invalid, but some things that were previously valid now become invalid. And this is what we've been doing so far, but they have the advantage that it's backwards compatible. You don't have to adapt your code, and you can still be part of the network. But they have some limitations as well, so that's why I want to deploy hard forks as well. So one category of consensus forks is unintentional hard forks or soft forks. Accident happens, there's mistakes in implementations. People don't always implement exactly the specification of the consensus rules, and accidents like this have happened in the past. Does it matter if they're soft forks or hard forks? Should we have different categories for them? I don't think so. We just don't want to do this, right? So the deployment recommendation is trying not to deploy this. It's simple. But what is the specification of the consensus rules that people aren't able to exactly follow sometimes anyway? So there's not really a specification. There's some documentation that claims to be the consensus rules, but it's usually outdated and doesn't go into enough detail. So one project that several people are working on, it's decoupling the consensus rules from Bitcoin Core, from the rest of Bitcoin Core, because the project is big and the consensus rules are really only a tiny part of that. So far we have exposed Verify script, which is kind of low level, but it's actually very good because with that you have there most of the crypto and the difficult stuff. But I would like to also expose Verify header, Verify transaction, and Verify block. And maybe, hopefully, eventually move this to its own repository apart from Bitcoin Core. And when we have that, we will have a formal specification that it's also the implementation, and other alternative implementations different from Bitcoin Core we'll be able to use. But we don't have that yet. So on controversial softwares, this is what we've been doing so far. I think it has been very successful. It's backward compatible, as we said, because if you don't upgrade to the new rules, it's fine. As long as miners have upgraded, of course. Because miners just won't mine the new blocks with that would be invalid with the new rules, and you will just validate fine. Here are a list of deployments that we have done, or in the case of BIP65, it's in the process, but I think it's very advanced. I don't know the percentage of miners that are upgraded, but it's high, I think. So the way we deploy this, at first we used just a time threshold. From this time on, the new rules apply, and then we started using is-block supermajority, which allowed miners to use the block version to coordinate the deployment. And people sometimes call this miner voting, but I don't like that, because it's not something that it's being voted here. These changes were supposed to be completely uncontroversial, and we were expecting all miners to be on board, so they're not voting anything. I prefer to call it upgrade confirmation. Just they are signaling to the rest of the miners that they are ready to implement the new rules. There's a BIP called BIP9 that supermajority has the limitation that you have to serialize all the changes, and we cannot deploy several of them in parallel. And BIP9 tries to solve that. instead of using the version field as an integer, we just use the bits individually. Specifically only 29 bits because 3 of them have been lost. Well, one for due to the fact that the field was a signed number instead of an unsigned, and 2 more because we used version 4 for the last one. But I think 29 bits. I don't think we will ever deploy 29 different consensus forks at the same time, so it's fine, probably. So uncontroversial hard fork. That's what we have never done, but I would really like us to do sometime. And here's a little list. There's many more things that we could do, but these are some of the less controversial, I think, and are easy to implement. So they are good candidates, I believe. In the current code of BIP99, it's only the time warp attack fix that it's implemented, but the other would be easy to include as well. So, well, I could talk a little bit about them. For example, I just mentioned that we lost 3 bits forever. We could fix that with an uncontroversial hard fork. Well, there's in the scripting language, there's operators that don't do anything, but just return true. But we can use them to deploy softwares, and there's a limited space, and we could have made that bigger from the beginning, but we didn't. We can fix that too, and recover more bits from the hash. So uncontroversial hard forks. The people want hard forks to be deployed slowly for all the implementations to have time to adapt their software. So, but we want to have a hard fork as soon as possible, right? Well, how is as long as possible, but long enough at the same time? 5 years? That's probably too much, I think. But I mean, I don't think anybody can see that 5 years is not enough time. And I don't know, we can go, I think 1 year would be fine as well, but we should think about that. So my deployment recommendation for this, and I know many people disagree with this, is using a temporal threshold like with this other times, and also use BIP9. And people don't like this because they say, no, in a hard fork, miners shouldn't have a say, or they shouldn't vote. But like I said, they are not voting. They're just confirming that they are ready because these are supposed to be completely uncontroversial. Miners are not supposed to oppose to these changes. If they did, then it wasn't truly uncontroversial. And for the temporal threshold, we could use the time in the header, but I don't like that much because you don't know if, for a given block, you don't know if the next block is going to be using the new rules or not. With the block height, you could know that, and it's very simple. That's the option I like more, but people don't like that because you are not able to plan very, very accurately. Like you can say 1 year from now, but it's not gonna be a 1 year. It's gonna be 1 year in terms of chain time. So 1 median block time year soon. So if people prefer to use the median time instead, and I think it's fine. But so that's what BIP99 is gonna be recommend, even though I prefer the height. So another category could be a controversial software that miners decide to collude between themselves, maybe not even doing any voting or any coordination, but well, yeah, they would do some coordination, but maybe not coordinating through the chain. And yeah, they could censor certain type of transactions. Maybe they just don't like amounts that are not even, and they censor all odd amounts or whatever stupid thing. And the deployment recommendation is, again, please miners, don't do this. And then there's hard forks that are controversial in nature. We'll see some examples if I have time. But yeah, the point here is here we don't care about miners, because if we accept that it's gonna be controversial, some miners may oppose to it, and then we don't need or we don't want to use any miner upgrade confirmation mechanism. We just can use a time threshold, and that's it. But it's a schism hard for it's kind of like going to war, and we don't want to kill civilians in a war, right? So here we don't want to hurt bystanders that don't know what's happening or don't know what the controversy is about. And a way to do that would be to start the controversial hard fork with an end version for the block that it's previously invalid. For example, -1. That has never been valid, and it's not going to be valid until you do a hard fork. So you can do that, and SPV nodes can tell that that block is invalid according to them, unless the rules have changed. So you force them to look at what's happening. So examples of hard forks. Like we said, miners could do things that users don't like, right? So imagine we don't have a block size at all, and we realize that we need one, but miners don't want, because for some reason they prefer bigger blocks. We could limit that with a controversial hard fork that miners may not accept, but it's fine. We won't accept miners bigger than X from now on, even if they mine them. We can do that. But if miners can do something against the users, like they could merge mine the whole chain and only with empty blocks, or I mean they could retaliate. But or they could do the controversial soft forks, and in those cases, miners are not in power of the rules of the network. If we don't like what miners are doing, we can just make their hardware obsolete by changing the hashing function and making their hardware, their ASICs, worthless. So I think that's one reason why they don't want to do this. They're in controversial software, because we could just change the hashing algorithm. Another example, let's imagine that some evil developers introduce an evil functionality in the code without people noticing, and then we notice, oh, they have done that. Is it irreparable? No, we can fix it with an uncontroversial hard fork, with a controversial hard fork, because maybe the evil developers that did it are not gonna agree with fixing it. That's another example. Another example would be spin-offs. Like there's some altcoins that their initial distribution starts the current UTXO of the Bitcoin chain. I mean, all altcoins could have been launched like this, and for example, Frycoin could have been launched at Frankfurt or wherever. I think not much would have changed. I mean, we don't have many users, that's true. Most Bitcoiners ignore us, that's fine. But I think if it had been a controversial hard fork instead, the result would have been practically the same. We just wouldn't have been allowed to change some things. or another example is just fundamental difference on what we want to achieve from the blockchain, with the blockchain. So there's some things that may be unavoidably controversial. But some question that, and I don't think this is very important, but I'll talk about it, because many people claim that in controversial hard fork, one side eventually has to surrender and go with whatever has a majority or the economic majority or whatever goes. And that's not true. You can be persistent or tenacious or stubborn, whatever you want to call it, and don't agree with the rules you don't want. And yeah, people can disagree for forever or for unbounded amounts of time. Some people deny that, but that's great because that's an example of something that it's an open disagreement, right? So people don't have to follow the majority, whatever you mean by majority. If it's miners, as we have shown, we can fork miners out. If it's user, you cannot even know about that because you cannot know how many users are using which software. And if it's the economic majority, whatever that means, it doesn't guarantee unification either. I will repeat the Fry fork example. Fry coiners would be still using the Fry fork chain if it was a controversial hard fork. Bitcoiners would have not moved to Fry fork. Some users like me would be using both chains. There's no reason why there always have to be a unification there. But I don't think that this point is very important because there's really lots of pressures to unify, especially if it's not very clear that there's a difference in fundamental values there. But yeah, I mean, even if this wasn't true, I think it's not very important. That's why I left it for the end. So if you have questions.
Yeah, we'll take any questions that people have. They should be technical in nature. Does anybody have any questions? No questions at all. Okay.
With a System hard fork, you would end up having the natural economic balance between the two forks based upon trading between them.
Yeah.
And I think that's an important point.
Yeah, that's an important point to factor with regards to the pressures for unification, right? But it could be that just one falls in price, the other doesn't, or it can be anything happening there. And in fact, in BIP 99 we mentioned that you cannot predict what will happen because you cannot predict demand for the two chains. But yeah, one way they could be unified is by one of the sides going to zero in the markets or near zero. That could happen, yeah.
Anybody else have any other questions?
Do you think it's worth differentiating between hard forks that are undetectable to SPV clients versus hard forks that are would require a global upgrade?
With controversial, maybe leave the microphone there, because with controversial hard forks, what we recommend is making it visible to SPV miners, and one might be a good reason to use BIP 9 with uncontroversial hard forks so that SPV can tell as well. I think it's something good that they always can tell that something's happening, even if they don't know what.
Any other questions? Okay, thank you very much for your presentation.
Thank you.
Next, we're going to have Adam back, who's going to be talking about fungibility and scalability.
All right. So I think everybody knows what fungibility means, that all coins are equal and interchangeable, and it's obviously an important property for an electronic cash system. If there's a breakdown in fungibility, all Bitcoin users start to have a problem. Bitcoin is unusual versus previous privacy technology systems in that it has fungibility without privacy. The previous electronic cash systems usually provided fungibility via cryptographic blinding. And in Bitcoin, that's achieved via decentralized mining, that somebody will process your transactions even if a given miner may not on policy reasons. There is some privacy because it's pseudonym-based, and there's some ambiguity from change addresses versus a payment address on the output side. And there are various things we'll talk about that are currently deployed or deployable. And the types of privacy that people might be interested in are a range of things. So the obvious one is linkability, i.e. who's paying who. Another one is the balance privacy, how many Bitcoins you have in your wallet. And the transaction privacy, how much was the payment value of a given transaction. So one of the main kind of point I wanted to make in this presentation is about the positive as well as the negative aspects of introducing fungibility mechanisms. So typically we've seen from fungibility mechanisms that they either increase the number of transactions or they increase the size of transactions. You know, for example, we've seen that the zero coin transactions are 30 kilobytes or thereabouts, and some of the mechanisms also increase the UTXO size as a side effect, which is also undesirable for sort of node size or scalability and performance and so forth. So the observation I wanted to make is that some of the more advanced fungibility mechanisms can actually reduce the number of transactions and also potentially reduce the UTXO size. So the obvious and simple fungibility mechanism is a one-use address. And so I'll just quickly recap what that does, costs and benefits. So it slightly obscures who is paying who, at least compared to a single fully reused address, as some of the earliest smartphone wallets used to do. It partly obscures the wallet balance because your coins are spread across multiple addresses, and people out on the network may not know that all of these addresses belong to one user, though often if you're using a smartphone wallet, the Bloom filter is actually not very privacy preserving, and so that defense is quite weak at present. It creates fragmentation, so it creates more addresses, increases the number of transactions, and it increases the average size of transaction because you'll be combining some of these fragmented values from your wallet. It also increases the UTXO size because each user will tend to have more unspent transactions as a result of the fragmentation. It's also only moderately effective, as we've had a number of academic publications analyzing the network and showing that the effectiveness of this approach is a little weak. So one thing that can be done to reduce the linking coming from having multiple inputs to the same transaction is to use merge avoidance, and that means to make multiple independent transactions from various addresses of the sender to various addresses of the receiver. So this is something that can be done, for example, at the payment protocol level. So something else that is buildable using the existing protocols and deployed in some places on the server side or even in a peer-to-peer format in the wallets is CoinJoin and the related CoinSwap. It's an improvement over one-use addresses. So you have shared input addresses from, just to recap how that works, shared input addresses from different users. So there's nothing preventing a transaction having inputs coming from different users. So it just combines the inputs from different users and ensures the outputs correspond to whatever payments the users would have made, combined into a unified transaction that pays each of the outputs and each of the change addresses. There are restrictions, so you need the values involved to provide actual ambiguity, which wouldn't by default have to be the case. Obviously, you gain no privacy if it's unambiguous as to who could have made a given payment due to the input amounts, for example. A disadvantage of this is you need to coordinate with other spenders, so it can slow things down. And it's also vulnerable to some kind of civil attack because some spenders may actually be attacking the system. So they may be offering to mix their payments with yours, but actually just trying to fill up the transaction set so that you're the only person that isn't the attacker. And these protocols are able to, in some of the more advanced versions, to be trustless. So the person operating the server, for example, or the peer-to-peer mechanism can't steal the coins, they can only stall it. Confidential transactions, so I mentioned at the beginning a number of different types of privacy. So confidential transactions are most directly interested in protecting the transaction value, so the amounts in the transaction from the observer. So it turns out that using some relatively conservative cryptographic primitives, basically the same mechanisms used by ECDSA signatures, that one can hide the values from the network. So it's the value of the transaction is visible only to the sender and the recipient, and yet the network can still validate what it needs to validate, i.e. that the values involved add up, the inputs add up to the outputs plus fees. So less obvious is that this mechanism provides some indirect privacy improvement. The change is more ambiguous because you won't see sort of $20 going in and $13.99 going out, with the rest probably being change, given specific amounts and the exchange rate. So change is more ambiguous. You could also just send preemptively zero-value transactions to other people, so that would add ambiguity that wouldn't otherwise be possible. CoinJoin becomes more effective because you can kind of get perfect coin joins. You can combine any set of coins with any other set of coins in a coin join, and it's fully ambiguous as to who's paying who without any extra restrictions on the input and output amounts. So now come to an example of the kind of trade-off here. So the transaction size with confidential transactions is maybe 6 times larger, depends on the number of inputs and outputs and so forth, and I have a new sort of small improvement that might take that to 5 times. So the argument is, well, would we deploy something like confidential transactions within Bitcoin main, and given that they're 5 times bigger and that uses block space that we might otherwise use for scaling, that presents a tough choice. So the point I wanted to make is that actually these transactions are providing more functionality per transaction. So they're in some sense, there's an opportunity there to compress in an indirect way. So a single CoinJoin confidential transaction or a single confidential transaction actually can replace multiple standard transactions, because you don't need to, so to the extent that these mechanisms are used, it reduces overhead. So you don't need to use merge avoidance. You can do that with a single transaction. You get balanced privacy, and some people have tried to obtain balanced privacy by intentionally splitting up their Bitcoin holdings into multiple HD wallet addresses. And similarly, people have done that for value privacy, like with merge avoidance or making multiple payments. And also you end up with a smaller UTXO set because you have less fragmentation in wallets. Now it's hard to evaluate the average reclaim space, but we might get closer to an acceptable new overhead or even neutral on overhead. And so we would need to do some kind of anonymized data collection with collaboration of users or something to work out the actual uses of these different types of merge avoidance and multiple addresses and so forth, because by design that's not always obvious on the network. Another type of fungibility mechanism is the linkable ring signature used in some altcoins. So it's slightly better than CoinJoin because the sender can choose the mix set and you don't need to coordinate in an online fashion. Unfortunately, the values being, each coin going into the ring sig must have exactly the same value, so that's quite restrictive in its usability. The linkability is what prevents double spending, and a side effect of these is that it's not UTXO compactable, so we get kind of ever-growing UTXO, and the overhead is the ring signature is linear in the size of the mix set, so you're going to choose, let's say 5 possible other inputs, and your signature will be approximately 5 times larger. There might be a small saving here, which is you're less reliant on one-use addresses for reducing linkability. So the other sort of more powerful class of fungibility or privacy mechanisms is the Zerocoin and Zerocash protocols, and these are relatively idealized. They hide the sender and the recipient. Unfortunately, they're not UTXO compactable, so you get an ever-growing UTXO set or double spend database. Zerocash hides the values. Zerocoin doesn't hide the values, so you have to, each kind of set of zero coins have a denomination, and you only have privacy within the denomination. And there is at least one, maybe several Zerocoin extensions that hide the value also. The Zerocoin transactions are quite large. It depends on optimizations and the security parameter choices. Zerocash is more practical on a size basis, but CPU expensive and using some very bleeding edge crypto, which we have less confidence in because of the short amount of time it's had for peer review and the relatively new types of assumptions being used. And both of those systems have a key setup trapdoor and various countermeasures to improve the acceptability of that. But otherwise, as I say, Zerocash is quite ideal for fungibility and privacy. Another type of fungibility mechanism that I proposed some time ago is an encrypted transaction, or previously called a committed transaction. And it follows the normal Bitcoin model that you can provide fungibility without privacy. So this doesn't actually provide any new privacy at all, and yet it improves fungibility. And the way that works is you have a 2-phase validation. So in the first phase, miners are able to tell that a transaction hasn't been spent, and in the second phase, they learn, who's paying, which address is paying which other address, and the amounts and so forth. And so the idea is that in the first phase, the miners have to mine the transaction, and the second phase happens, let's say, a day later or something. And in the second phase, all the miners learn an encryption key, which allows them to decrypt the first phase transaction, tell that it's valid, and then do the final stage approval. And the advantage is that there's a deterrent to censoring the second stage transaction, because the first stage is already mined, and basically the protocol can have a consensus rule that you have to approve all valid second stage transactions, otherwise your only opportunity to mine would be to try and orphan the entire day's work, which is quite expensive. So a related topic with fungibility is the sort of trade-off with privacy and identity. So Bitcoin is a intentionally identity-less system. So it's permissionless, and you can operate it and sign up and use it without an account. You don't need to register anywhere. And so I think what we want to achieve as a kind of design target for internet protocols in general and for Bitcoin is to avoid it being trivial to do preemptive mass surveillance as a default, i.e. investigations are always going to be possible, but as long as there is some kind of incremental cost to conducting an investigation, we can retain societal norms. So, you know, some people have tried to argue against privacy features in electronic cash on a basis, you know, to improve privacy in Bitcoin on a basis that that would make it, you know, too anonymous or something. But I think that's not really a concern overall, and I spent quite a bit more time talking through the reasons for that in this linked video in the past. So I'm probably running fast here, but anyway, so a summary of the trade-offs here that I wanted to make to say that some of these advanced fungibility systems might be more deployable than we previously thought, because you do reclaim some space ahead. So the high level is that to evaluate it, we actually need to consider more than just the raw size or space overhead. We also have to consider the delivered fungibility and the savings in UTXO and the number of transactions that would otherwise have been used, because we're introducing a new, more powerful type of transaction that can potentially replace multiple simpler transactions or transaction usage patterns. To actually evaluate that and put some numbers to it, we would need to collect anonymized data about the usage patterns and overhead, how common, you know, coin join and merge avoidance and so forth are. Or another way to look at it may be that you know, people are making do with very little privacy where that they would actually prefer more privacy. So perhaps they're willing to pay for it if it were available. And so at least it would be good to provide an improved range of trade-offs for users so we can find out what they would pay for, what they would like to use. Some users may be willing to pay more for privacy if it's available. And some other users, you know, sort of high-scale, low-value transactions are presumably not typically as sensitive to fungibility because they have, you know, just some micropayments at stake. If those got subjected to some kind of policy or lockup, it wouldn't be that affecting. They could just like forget about the small amount of money they'd put into it. So overall, we want to improve flexibility and allow users to make economic choices. And fungibility itself is very important and a core part of the permissionlessness of Bitcoin. So I think we do have some work to do on fungibility. Bitcoin's fungibility definitely do with some improvements. And in summary, it's my kind of conclusion that fungibility solutions are more practical than we'd otherwise think if we also take into account the reclaim of transactions, number of transactions and transaction usages from the simpler methods people are using at the moment. So that's the end of the presentation part.
Okay, thanks, Adam. We'll now take technical questions.
Over here. Go ahead. You're next.
Hey, would you agree that that chaining several CoinJoin transactions improves CoinJoin in general and the privacy behind it? And with confidential transactions, would one CoinJoin be enough to completely break the link of coins? Thank you.
I guess chaining CoinJoins presumably helps, and a confidential transaction CoinJoin is more powerful because you have to wait, you know, you can choose any set of transactions. You don't have to wait for qualifying ones that have an ambiguous range of values. So in general, it improves the effectiveness of CoinJoin, and you can also mix in, you know, zero value transactions as well as a secondary method.
You had talked about Zero Cash being kind of a nearly ideal solution with a couple of caveats around it. You know, one being the processor cost and the other being a risk around new crypto. Both of those issues seem like they solve themselves over time. The question is how much time? So how much extra CPU, you know, do they consume compared to normal transactions, and how risky is the crypto in terms of how long do you think it would take before people started to feel comfortable around the security of it?
Yeah, so the next speaker may have some things to say about this, but I think the CPU cost, obviously CPUs become more efficient, so that will partly improve itself, and perhaps we can sort of combine a hybrid between smartphone wallets and desktop servers to improve some of the performance, but the crypto protocol is kind of more difficult because it depends how conservative you want to be. So the Bitcoin existing crypto assumptions are extremely old assumptions, 20, 30 years old, and so we have very high confidence in them. Whereas the Snark crypto and even, the Well pairing has been around for a while, but not as actively used. Like 20 years, but not as actively used. So we don't know as much kind of practical applied research has gone into attacking them. And then there are these all new assumptions that go into them, and it's also a very rapidly evolving space. And the other challenge that I mentioned is the sort of setup trapdoor. The person setting it up has a private key of some kind that they should delete. So there are some variants that don't have that problem.
We have a question from IRC. Which of these proposals would be more likely to have BIPs written in the near future?
Interesting question. Perhaps confidential transactions is closest in that is actually implemented within the sidechain elements open source release, so people can look at that. Also, potentially, if the protocol can have its space overhead lowered. So I have made some progress and made a 24% space overhead reduction. If we can get a breakthrough on that, that might bring the viability forward for integration.
我有个问题。
There's one at the back.
我这里有一个问题哈，我知道 Blockx 最近是做这个侧链的是吧？然后呢，这个侧链其实对解决这个比特币的扩展性还是有很大的帮助作用的。然后但是我发现那个在侧链里面也有个私密交易叫做 confidential transaction， 但是这样的交易。
等一下，我先说一下。So Blockstream does side chain transactions, and side chain transactions helps with the scalability. But inside some side chain transactions, there are some confidential TXs. 你继续吧。
但是那个就是说这样的私密交易带来的这个就是说容量的扩张可能也是比较就显著的，就是说带来这个交易的字节数的增长也是比较显著的。所以如果说是在侧链里面太关注这个隐私的话，是不是会导致这个对解决比特币的扩展性没什么帮助？
So the question is, in sidechains, if we're too emphasizing on confidential transactions, does that limit the scalability of sidechains for Bitcoin?
So in the sidechain elements alpha, the confidential transaction is default, but you could disable it. So it's an optional feature and not, you can have sidechains without it. As I was trying to articulate in the presentation, even though the average transaction goes to 2.5 kilobytes or potentially 2 kilobytes with some more recent, not yet implemented improvements, it is providing more value, more functionality per transaction. So in general, you should need less transactions, so the overhead is not as high as it sounds. And we've heard, a range of users have seemed quite interested in it. The financial institutions that are thinking about share-related uses for blockchains are also quite interested to see some kind of commercial confidentiality. So it seems to be something that's in demand across the full set of Bitcoin users.
Okay, who has the next question over here? Raise your hand if you have more questions.
In encrypted transactions, there's 2 steps, and the second step is the one I'm afraid that miners will censor, right?
Yes.
So what happens if I never publish the second step, and they cannot mine a valid block?
Yeah, so I skipped over the details there. So it's time lock encrypted, and it has to be provably decryptable at the time you publish the first phase. So that means if you publish it and then you fail to publish the key, then anybody can decrypt it. It just takes a sequential execution on a CPU core.
So, can I talk about the anonymization? If you do that kind of anonymization, it emphasizes that 6 times larger of the blockchain size will be 5 times improvement. The question is, if there are less, if there are less full node wallet users, and even if there are more miners, it won't be very helpful for me. Both, if there are more valid blockchain copies, and then there will be better the security. More miners doesn't mean any helpful. Not everyone can. Not everyone can afford such a large amount of gigabytes, and if most of the transactions to the users are useless, and at most they can have the Bitcoin to be security. And anonymization for now is good enough, and I don't really believe that.
What is your question?
Sorry. How can we ensure that everyone with the blockchain, valid blockchain, will be continue to use the Bitcoin full node wallet under the anonymized Bitcoin blockchain? The 6 times larger blockchain.
Right. So, it is a trade-off, and so mainly I was arguing that the overhead is maybe less than it seems at first, because we say, oh, it's 5 times worse, that's too much, we can't use it. So if we go and do the analysis and find that, in the best case, while each confidential transaction would replace 5 regular transactions, then maybe it could be the same overhead, and that would surprise us. Now, probably it's not as effective as that, but that's an interesting situation. So, if we can collect the information about the amount of transactions, the amount of fragmentation in wallets, and the amount of extra transactions that arise purely from attempts to get value privacy, it can give us an indication. And also there is hope that we can improve the space overhead of confidential transactions. So we've already recently managed to reduce it from 6 times from 2.5 kilobytes to slightly under 2 kilobytes. If we can reduce it, quite a bit more, and while it still remains larger than a standard transaction, we can maybe estimate the amount of regular transactions it can replace to provide the same or better functionality to users. So it may be that it's not yet practical to deploy something that's 6 times larger, particularly right now, but it shows that there might be a crossover point where if we can make the size of the size of a confidential transaction smaller, and we can go and measure how many regular transactions it would replace in functionality terms on average, then we can make a case to deploy it sooner than people would otherwise expect, even within the main chain rather than in opt-in side chains.
Let's thank our speaker. And next up is Madars Virza, who's going to be telling us about zero-knowledge proofs for Bitcoin scalability and beyond.
All right. Hey guys, I'm Madars from MIT, also affiliated with Zcash. And today I'm gonna tell you about zero-knowledge proofs for Bitcoin scalability and beyond. Even though this is an overview talk, many of the results I'll be telling you about are based on joint works with people you see on the slide. Some of them are even here at Scaling Bitcoin. So let's begin. A quick outline for my talk. First, I will give a very brief introduction to zero-knowledge proofs. And then I'll try to convince you that if you care about Bitcoin scalability, you should definitely care about zero-knowledge proofs, and you should keep them on your radar. And if you're convinced of that, then you should be asking yourself, where can I get those zero-knowledge proofs in practice? So the last part of my talk is going to be zero-knowledge in practice, where to get zero-knowledge proofs, how to program zero-knowledge proofs, and how to deploy zero-knowledge proofs. Okay? So I'm going to start by introducing zero-knowledge. It's a very beautiful notion by Goldwasser, Micali, and Rakov, developed in late 90s, late 80s, and it concerns the following three objects: a relation, a prover, and a verifier. Relation is just set of pairs, instance, and witness. And if it sounds intimidating, then consider the following example relation: the relation of circuit satisfiability. The instance here is a circuit, and witness is the satisfying assignment. And instance witness pair is in the relation if and only if the circuit outputs 1 on the input. Okay? Both prover and verifier know the instance, in this case the circuit, and prover additionally knows the witness. And prover wants to convince the verifier that he knows the witness. So verifier will begin to interrogate the prover, ask a question, get a response. Ask another question, get another response. And it goes on, and finally verifier gets the final answer from the prover and either accepts or rejects. We want the following three properties from this. First, if it's indeed the case that prover knew a valid witness, then the verifier will always accept. Of course, if the prover didn't know a valid witness, then he cannot make the verifier accept. And finally, and most interestingly, we want just given this interaction, the verifier learns nothing about the secret witness the prover might have had, other than the fact that this witness exists. So in our case, the verifier would not learn even a bit of what made the circuit accept. Okay? So those are zero-knowledge proofs, interactive, but they become even more useful when they are non-interactive zero-knowledge proofs. Meaning that prover sends just one message, proof, to the verifier, and the verifier either accepts or rejects, just as before. And it's very useful because then the prover can post this proof, say, on Bitcoin blockchain, and later go away. And nobody needs the interaction with the prover again, and everybody can verify the proof for the rest of eternity. Okay? So this is a formal notion. But in fact, what I have told you is a little bit of a lie, and it is impossible for interesting languages if you don't allow yourself any kind of help. However, if it becomes possible if you let a trusted pre-computation just one time and outputting a string. That's called a common reference string. And so here's how it works. There needs to be a trusted generator that rolls some dice, outputs a CRS, the common reference string, and then goes away. And this trust is required only once. And after that, prover and verifier can many times use CRS to prove statements and verify them respectively. Okay? So this might sound very abstract, but I will motivate with examples how this is useful for Bitcoin scalability. And in fact, my claim is the following, that many scalability problems in Bitcoin world can be traced back to questions about privacy. For example, if all transactions are public, then receiving a wrong change for coffee could taint and devalue your coins, because later you cannot go, say, to exchange, because it's prohibited by the government from giving you money. Another example, solvency. If exchanges can claim that proving solvency is a privacy liability, then they can just shy away from doing this, and you get distrust in traditional service providers. Also a scalability issue. And similarly, questions even about minor centralization can be traced back to questions about questions about privacy. So my claim here today is that zero-knowledge proofs can be helpful for all of above, and I'm gonna quote-unquote prove my claim by example. I'll choose the fungibility and solvency examples, and so show you how to use those zero-knowledge proofs from previous slides to solve them. So starting for fungibility, I'll show how to develop a currency that's completely private. And this is based on a scheme by Sanders and Tashma. And let's suppose we have a traditional Bitcoin blockchain, and we want to have a anonymous currency sitting right next to it. Let's call it anonymous coin. And to do that, we will introduce a new transaction type called minting with the following semantics, that minting destroys one Bitcoin in the Bitcoin world and creates this one anonymous coin with a coin commitment CM. And that CM is just going to be a hash of serial number and a nonce. Okay? So you can go on and like destroy Bitcoins and create those wonderful anonymous coins in this bubble, but well, that's not very useful, is it? So what you do next is you need some way how to spend those coins, presumably in private way. Well, one way how can I spend a coin is just I choose one of my anonymous coins from the nice bubble, and I publish its serial number and nonce. Okay? And it obviously doesn't work because then you can compute the CM and you immediately see from which Bitcoins that coin came from. So this doesn't work. What does work, however, is doing the following trick. You construct a Merkle tree over all of the coin commitments in your wonderful bubble, and then you publish a serial number plus a zero knowledge proof. A zero knowledge proof of the following statement. There exists a nonce such that when you compute the coin commitment of the serial number and nonce, then the coin commitment is indeed in the Merkle tree you just computed. Okay. And you can see that this first is private. Serial number doesn't reveal anything about where the CM came from. Proof doesn't reveal either because it's zero knowledge. So this transaction is completely unlinkable to the original Bitcoins that was spent. Yet, zero knowledge proof ensures integrity. You definitely know that there existed a coin in this anonymous bubble that was spent. Moreover, you can only spend this coin once, because if you tried to spend a coin from the bubble twice, you would publish the same serial number twice, and you would be immediately caught. So at a very, very high level, this is the basic idea that's behind Zerocash, which builds upon this, adding direct payments, divisibility, and so on. But basic idea remains the same. You'd have a ledger not of transactions, but a ledger of proofs that a valid transaction occurred. Okay. So that's one useful example of zero knowledge proofs, but there are others. For example, I'll show a very, very brief overview how to use zero knowledge to have privacy-preserving proofs of solvency. And here, by solvency, I just mean the simple claim that my assets are greater than my liabilities, and privacy-preserving should mean that exchange should not reveal anything about its keys or balances. Okay. So all of this is a 10,000 feet overview of wonderful work called Provisions, for which also authors are here. And Provisions works as follows, that you need to publish two commitments, one commitment to all your assets, one commitment to all your liabilities, and then three kinds of zero knowledge proofs. First, you want to claim that exchange is solvent, meaning the value that's hidden under the asset commitment is greater than the value that's hidden under the liability commitment. But of course, this is not enough because anything could be in those two commitments. So what you're doing next is you prove that the liability commitment was actually correctly formed, meaning that each account balance that you have for your exchange is included in total liabilities. So let's suppose we have a table of all users for my exchange, and I will do the following now. I will publish commitments to all balances. They are hiding, so nothing wrong here. Then I will go to each of my users and prove to user I that I's commitment opens to the balance that the user supposedly had at my exchange. And finally, proves that the commitment of all liabilities is consistent and sums up the values that are hidden in all the user balance commitments. Okay. And that's it. That's how I prove liabilities. Of course, finally, I need to prove that I control the set amount of assets, and I will do this like this. I will first choose a large anonymity set of public keys say, the entire set of public keys that are available on Bitcoin blockchain and associated balances. And then I will try to prove knowledge of private keys for a subset that can open up at least the asset Bitcoins. And of course, zero knowledge proof is quite involved, but you should believe that this can be in fact done. And there is a way how to prove solvency in privacy-preserving way. So 2 examples, getting private transactions or getting private proofs of solvency have demonstrated us that zero knowledge really seems to be something really useful. So we should go and see, can we implement zero knowledge in practice? And I'll tell you right about that. Okay. So first, I'll tell you about 2 kinds of zero knowledge proofs. There are classical non-interactive zero knowledge proofs called NIZICs, such as Schnorr proofs or the range proofs used in confidential transactions. And those proofs have been implemented and they have even been deployed, but classical NIZICs sometimes can be inefficient. Meaning, unless your statement is highly structured, then the proofs can be long as time to decide the membership in the relation and hard to verify. There is a different cryptographic primitive called SNARKs that address the inefficiencies of NIZICs. Meaning, compare the red and the blue, the proofs are short, constant sized. In practice, it's like few hundred bytes, and easy to verify. In practice, it's usually milliseconds. That said, this power, namely succinctness, comes from somewhere. And this somewhere is cryptographic assumptions. Like NIZICs require more traditional cryptographic assumptions. They are sufficient for them, while SNARKs rely on stronger cryptographic assumptions. Moreover, NIZICs and SNARKs differ in the way how you generate the CRS that I talked about before. For SNARKs, the CRS, for NIZICs, the CRS is typically simple. The CRS generator just outputs random coins, and well, heuristically, you can get randomness, say, from hash functions or from sunspots or whatever. While for SNARKs, the generator outputs a common random string with a lot of structure. It's complex, and you really need somebody to do it. So it's a deployment challenge. But we'll see later how to address this deployment challenge. That said, we really like the efficiency of SNARKs. They can be orders of magnitude more efficient for general NP statements. So for the rest of the talk, I'm going to focus on this cryptographic primitive. Okay. So do those SNARKs exist? They seem to be very strong, very powerful. The answer is yes, and we have a beautiful line of research that has produced theoretical constructions starting from 90s, and some of the most modern constructions are even efficient enough that they're working prototypes from various groups around the world. And even better, most of those prototypes have full source code available online. So you can go to those links and get a SNARK system. So SNARKs exist not only in LaTeX, they also exist in code, but even more, they exist in the implemented systems. They are feasible for certain applications, such as Zero Cache or Hawk. So SNARKs do exist. I can go get their source code. So how do I program a SNARK? I have a relation in mind. What do I do? Well, there is a bit of a challenge, and the challenge is representation. That relation I probably have in mind is high level. It has hashes, Merkle trees, digital signatures, and so on. While the relations that my SNARK understands, or the implemented constructions understand, is typically something like circuit satisfiability. And the question arises, how do I get from my relations that I have written, say, on a piece of paper to an actual circuit, gate by gate, that it checks it? But this is a solved problem, and there are essentially 3 solutions how to do that. Number 1, there is this so-called SNARKs for C approach that essentially mimics the early days of computing. That is, you first pick a CPU and write the transition function of the CPU in a circuit and use the transition function to write universal circuits that can decide any program written in for the CPU. And then you take your relation and you write a C program for your relation that decides it. And finally, you compile your program down to assembly, and this assembly is something that your universal circuit can eat, so you feed it in, and all's happy. But this approach is probably the only approach that I know that can give you universality or bootstrapping or whatnot, but it also can be quite inefficient because for each step of the computation, you need entire CPU to be laid down in the circuit. So if your computation is sufficiently specialized, you can use a different approach that's called program analysis approach. You basically write your program that decides your relation in a restricted subset of C. For example, your program must have all of its memory accesses known at compile time. But if it's the case, then there exist very nice circuit generators for such restricted subsets that directly give you a circuit. And given the circuit, you can directly feed it into the snark. Okay. And finally, there is this approach that we call the gadget domain-specific language approach, which is essentially writing subcomponents for your relation by hand as circuits and then composing them together. And you can imagine like being an electrical engineer and placing on your circuit breadboard like a component for SHA-256 or a component for snark verifier or, I don't know, elliptic curve arithmetic component. And it might sound a little bit crazy writing all those components by hand, but the good thing is that it only needs to be done once. And for example, the library we have been writing, libsnark, has lots of pre-written gadgets of this kind. So you can probably use a gadget approach. Okay, so there are three approaches, but that's quite a bit of a slide. Which one should I choose in practice, and what should I do in practice? So, in fact, what is the typical practical efficiency for snarks? Well, the verifier efficiency only depends on the input of your relation. Usually when you structure your relation right, it's typically milliseconds in practice. The bottleneck tends to be prover performance, which is essentially the base snark performance, the better snark, the faster or something, applied to the size of the circuit. If you can write a small circuit, then very nice, you get a efficient prover. But what does it mean in concrete numbers? Well, there's a paper about non-outsourceable process that puzzles that did benchmarks for provers for a 500,000 gate circuit. Say one snark system took about 20 minutes, one snark system took about 30 seconds. But, okay, that's great, but what can I fit in this 500,000 gate circuit? Well, concretely, we went ahead and implemented SHA-256 cryptograph compression function, which is a useful primitive to have, for example, in Merkle trees. And if you write it down as a snarks4C approach for say, tiny RAM, then in 500,000 gates, you can probably fit 0.08 of those compression functions. So, no. But if you just use the circuit generator, you could fit about 8.1, and if you write it down using gadgets, you could probably fit around 17. That means that in 30 seconds, you can prove something really non-trivial, like 17 evaluations of hashes. That said, you cannot prove everything. You cannot, for example, just say, let's throw snark at it, and the snark will take as its input entire Bitcoin blockchain. It simply won't scale. So the crucial thing for efficient use of snarks is what we call relation engineering, meaning that your relation should be really checking local properties. You should use non-determinism, and you should consider snark-friendly crypto. Someone's telling that I should wrap up, so I'm going to tell you about the most exciting part of my talk, which is deploying NISX and snarks. So let's suppose you have your NISX system our Snark system and you have implemented it and there are proofs and verifiers running all around. And the question is, how do you deploy it? That systems no longer sit in confines of a single corporation, they sit all around the world. So who in practice generates this common reference string for your system? Who is the person that's trusted by absolutely everyone in the world? Well, clearly there is no such person. So does it mean that Snarks cannot be deployed? Well, let's see what are the consequences of a bad CRS. Number one is that zero knowledge still holds. For example, if zero cache setup broke, then transactions would still be private. Unfortunately, Sounders breaks, meaning that adversary can start proving false statements. In fact, some uses of Snarks are not consensus critical. For example, Peter Todd's proposal for faster block propagation is just sending a block header plus proof that there exists a block. And in this proposal, if you get a bad CRS, you probably just get a couple of lost blocks, but long-term durability is going to be okay. But still a question, can consensus critical Snarks be deployed? And the answer is yes, and I'm going to show you how. So ideally, we'd like this, that there is this wonderful Snark generator with Halo on its head, who generates a perfectly valid CRS and goes away, and doesn't leak anything about the coins he tossed or anything. And the CRS is completely secure. But of course, we cannot have this one person that's trusted by everyone, so we are going to do what we do and decentralize all the things. We are going to have a decentralized protocol for Snark setup that will have multiple parties in it. And those parties will pass messages, and out comes the CRS. And we'll require that our protocol produces the same thing that our idealized generator would have produced, up to n-1 corruptions, meaning that if at least one of the participants in the protocol is honest, then the CRS is fully secure. And in fact, we have designed a protocol that does this, and it is reasonably efficient. It's not the most efficient, but you can probably tolerate it. And you could even imagine like a large ceremony with all of those people participating. And everyone in this room probably trusts at least one of those guys, but not all of those guys. But as long as you trust that at least one of them is not talking to anyone else, you're fine. And those guys talking to each other, you're right. So to conclude, many scalability problems can be traced back to privacy, and Snarks can help. More precisely, zero-knowledge proofs can help. And people sometimes say that generic zero-knowledge crypto is like 10 years away crypto. And I think it's completely false. It was 10 years away crypto 10 years ago, and it is feasible today. It can be programmed, it can be deployed. And in fact, if you want to be part of it, then one of the teams that's working on zero knowledge, the LibSnark team, is putting out a call for collaboration. We need all kinds of contributions, security audits, performance enhancements, and so on. So visit our webpage and help us out. So I hope we build nice zero knowledge systems and make Bitcoin more scalable. Thank you.
Thank you. We'll do a quick Q&A session. Question, raise your hand, please. Okay, question right here.
So can you go back to the slide with the three options to the for implementing it?
Yeah.
So I mean, the question is, it seems like the latest approach of the widget is you can combine that. Couldn't you combine one of the other two with that to generate a gadget and then?
It is correct that the gadget approach can in fact be combined with, say, program analysis approach. So you can do the heavy lifting of the hash function in gadgets and then do the generic parts that probably have nice circuit implementations, just write them in C. And in fact, I know that team from University of Maryland is about to release a compiler that does this. It combines gadgets and program analysis.
So I want to talk about if I want to, what can I do with the zero knowledge proofs to create something assets in my physical region? Can I use it physically? Can I is that just like creating a crypto-backed fiat money? And with that, where will be the hidden record stored and somewhere else, or to prevent?
So if I understand correctly, you're asking if all the transactions are private, who stores the information about values, and all the individual participants in the system would know the values they control, but the consensus participants would just know that the valid transactions existed. So you would need to maintain your wallet. And
if I can use it physically, how can I do it?
I didn't really get this, so maybe we can take this offline.
I see you have Snark Verifier in your Gadget DSL. How well does that work?
So this was Crypto 2014, and I think this has been in GitHub repository since like January of 2015. So Peter's asking essentially for recursive snarks, and do we have verifiers for them? And the answer is yes, we do, and you can do bootstrapping and recursive snarks. So.
Just a reminder, we're not going to mention any names, so no attribution.
Okay.
I misspoke.
So on the other slide, you had, I think, the proposal by Peter to do block verification in a snark, essentially, or send that along so people know that the block exists or is valid. Do you think that's feasible today already, or have you guys done any testing on that?
So we haven't tried implementing this, and if you wanted to just take a snark that reasons about an entire block, I would say it's probably not efficient enough to be deployed. Maybe the part where you verify individual transactions individually and then use bootstrapping to create a tree of proofs, maybe that could work. But I cannot tell for sure if the numbers are going to be good.
Hi, I'm sorry. When you were talking about using zero-knowledge proofs to prove solvency, was that through going through the same process, whereas you actually have to burn a Bitcoin to prove that you actually have the private keys for them? Therefore, if you actually had to burn them, then I just didn't connect how the proving process of your solvency didn't actually just move your Bitcoins off into these CMs, which then need to be retrieved somehow.
So if I understand the paper correctly, the author in the audience is that it justifies us to use non-interactive zero-knowledge proofs of knowledge, which means that if you have produced a proof, then you must have known the secret key, and there is no other way for you to produce the proof. In fact, it can be extracted from you if from a malicious prover that can produce such proofs. So there is no need to move Bitcoins around and and burn anything.
Do we have any other questions?
Okay. Last question.
Hi, Manders Swix. Short question. You was talking about the anonymous Bitcoins. So, and post question. So, then you're talking about the destroying coins. I'm pretty suspicious about any destroying of the coins or modifications which are staying on the endpoint. So, there is a lot of much simpler methods to make the anonymity for Bitcoins, like Bitcoin mixers. You can just send and get coins. It's much simpler. It doesn't require the protocol extension. And if it's simpler and works simpler, why we need any extension to make these anonymous coins?
So there is a trade-off between the anonymity you get and the protocol modifications you need. For example, for mixers, you're not fully anonymous. There is still some knowledge left in the system about where the coins came from and where they went. For a system like this, anonymity is much cooler. Your anonymity set is everyone in the system. So if you think that you need this kind of anonymity, well, the cost for it needs to be burned somewhere. So yeah, but I guess that lesser anonymity can be obtained with simpler methods too.
Okay, we'll take one last question.
Okay.
Is there any way that we can frequently update the CIS? Because it may happen that when I know all the people who generate the CIS, I can just go and bribe all of them.
So the system that we have does not let you update the CRS. So if n people come in the room and they generate a CRS, then you kind of just take this CRS and mix in your randomness as an n plus first person. So the setup would need to be done again. So that's a limitation of the setup procedure.
Okay, so that's all the time we have. Let's thank our speaker. So now we're going to have a 10-minute break because Madar's went over and went into your coffee time. So 10-minute break, and we'll resume. Yeah, it was worth it. Okay, great. Coffee time, break.
Sorry, Neha, there's a lot of back and forth. I can do the chat. I don't have my stuff, but I can do the breaks. I was going to do the breaks, but then there's like, last question, one more question. I know. One more question. Yeah, it's okay. But I saw you get out.
Yeah. So. He did run over, but he said his name. Oh, the speakers are public.
Are we allowed?
The speakers are public. They're like on the website. Yeah.
All right, so we're allowed to tweet
Next
out.
time I'll mention it. No, someone named
Not
Paul.
Paul. Mr. Snow.
Actually, you can.
Do you want to sync up over coffee the next round?
Yeah.
Hello everyone. For coffee, it's the other way. Look at the stage to your right. Look at the stage and then to the right side, please.